control the particle size. I may want to produce large number of particles, small size, or I may want to produce really huge crystals and very few in size. Both are important. For example, in silicon industry, you grow a single crystal of silicon as tall as me and as fat as me. Only one crystal. It's cut into wafers. All the electronics chip that you talk about are made by that. But for nanoparticles, which I am going to talk about, you want a large number of crystals, only small size you want. So, how to do this? So, one procedure is to make supersaturation very large. Okay. It is so large that growth is not able to dominate for a while. Then you got large number of crystals. You can start out with small amount of material. So, particle size is very small. You can also do one more thing, that is starve the particles, give only a little bit of amount of material, then also particles will become small. But it's a bit more complex process, because if you make this C naught by Cs small, you can make amount small, but nucleation rate also becomes very small. So, it's not a good alternative. The alternative is to keep large, G large, but make V small. Volume of the reactor is very small, concentration can be high, but the amount is still small, because you took a volume very small amount. So, you got a small number of particles. These are the various strategies by which you can control particle sizes. So, I am going to use all this qualitative knowledge which I explained to you to explore the plenty of room at the bottom. I do not know how many of you recognize this gentleman here. This is Professor Feynman. He is a great physicist, a magician if you like, and he is the one first told about the world at the bottom of the scale, length scale. What is at the bottom? Everybody wants to do universe, galaxies, everything. That is the fashion. But Feynman told you as to what all the magic you can do at the smallest time scales. He wrote a very, very great paper on nanotechnology, what all can be done with small particles. So, he called this plenty of room at the bottom. He delivered this lecture in 1959. Okay. Today, we are talking about nanotechnology. He had this vision to see where great technologies can come so long ago. So, I am going to talk about production of gold nanoparticles, as nano size implies to you. They are 10 to the power of minus 9 meters, about 10 times as large as a molecule. There are many applications of gold nanoparticles. You can functionalize them, that means activate the surface, and you can use them to detect DNA. They are markers. You can embed gold nanoparticles inside a body. They can be target for radiation, for cancer therapy. They can also be functionalized, they can be used for drug delivery. So, there are so many applications of nanoparticles. Now, I want to produce them. Size is very small. What can I do? One is to make reactor volume very small. That is one method. These are called micelles. They are like 10 to 20 nanometers liquid pools. So, reactor volume is very small. So, you can produce nanoparticles. I am not going to talk about that method today. You can make G large by using bulk precipitation. So, I can use thiols, I can use citrate, I can use ultrasound. Today, I am going to talk about the citrate method, which is a very old method. Now, before I begin this, I want to tell you one thing. I would like you to observe very carefully my methodology. I am going to follow what is in Levenspiel, which everybody here should know. That is classical chemical reaction engineering approach. What is it? You first list the chemistry. Okay, you try to understand what the chemistry is doing. Then you write equations, chemical equations, A plus B goes to C, whatever. Then you get the rates, rate of the chemical reaction. Then you put them in mass balances, they are called design equations. You solve them, you get design curves. This is sum and substance of chemical reaction engineering. This is what I am going to do exactly here for you. I am not going to use anything more than what is in Levenspiel. Okay, that is what I want you to notice. We start with citrate. Citrate decomposes, giving you 2 electrons and a compound called dicarboxyacetone. Please remember this dicarboxy. Okay. So, this is going to dicarboxy and 2 electrons. These 2 electrons are used to reduce auric chloride to aurous chloride. Valence has dropped by 2 to 1. This aurous chloride undergoes disproportionation by itself, we do not need to do anything at all, produces gold atoms and auric chloride. Now, this reaction is very well known to chemical engineering people in a different context. It is catalyzed by gold particles. Okay. If a product is catalyzing a reaction, is called autocatalytic. The rates will exponentially increase because the product is catalyzing your reaction. So, you can see I can use proper concentrations, make this reaction go very fast, then autocatalytic reaction takes over and produces gold atoms at a very rapid rate. So, I can increase the supersaturation very rapidly by this method, by a combination of manipulating concentrations and using the autocatalytic method. So, that is the overall chemistry. Now, this dicarboxyacetone is an organizer, it is a nucleating agent. I told you how metal atoms can be nucleated by organizer mechanism. So, the gold particles are stabilized and organized by dicarboxyacetone, that is a product of citrate decomposition. Okay. But there is one bad thing, dicarboxyacetone also decomposes and gives you useless carbon dioxide and acetone and hydroxyl ions, which are of no use to you. Okay. I want you to notice one thing, a very important compound to me, nucleating agent, is B. It is coming from A citrate, and C is this acetone, which is a useless product. A goes to B, goes to C. This I am sure all of you have studied in Levenspiel. So, we study A goes to B, goes to C, A goes to B, A goes to C, because they are models of very wide number of reactions. You study them, you can learn a whole lot. Okay. So, the citrate process is like this. Citrate reduces gold and yields dicarboxyacetone. Dicarboxyacetone also organizes gold atoms. It also stabilizes gold particles. This is also lost. This is the sum and substance of the chemistry of the process. Now, there is a design curve for the process. This design curve is obtained experimentally. So, let me tell you how this is used. I am plotting here diameter of the particles, and here the control parameter is the citrate to gold atoms ratio. I want nucleation, therefore, citrate is important, raw material gold. So, ratio of the citrate to gold salt is a control parameter. So, you plot the result versus control parameter, that is the design curve. I want to produce this particle size, I go here and select this ratio of citrate to gold. I run my batch reactor, in the end I got that particle size. This is how a design curve is used. Now, you see the volume of the particles is increasing by 1000-fold when I change the citrate to gold ratio by a factor of 7. So, why is it such sensitive change? The sensitivity is in the beginning, afterwards is flattening out. Why is it sensitive in the beginning? Why is it flattening out afterwards is really what I should explain. Okay. So, I got a qualitative explanation. Citrate or indirectly dicarboxyacetone is increasing the nucleation rate because it is the organizer. Therefore, if I increase citrate, more dicarboxy, less particle size. So, initial drop is coming because of that. A constant fraction of dicarboxy is also being lost. A goes to B, goes to C, which I was explained to you. Therefore, it reach a peak. Okay. If that peak is coming after growth dominates, then it is ineffective. So, balance between rate of nucleation and degradation of dicarboxyacetone is a key, because it is producing a maximum. This A goes to B, goes to C, is producing a maximum. I want it to occur well after growth dominates, if I can manage to do it. There is also one more factor, the sodium coming from citrate. Citrate is a salt that destabilizes the particles. There is a side effect which only people, if you know a little bit of colloidal chemistry, will know, that promotes agglomeration, making the particle size go up towards the end. I do not want you to pay so much attention to it, but the first three facts are the most important to us here. Now, I want to predict that curve. What are chemical engineers wanting to do? They want to write equations, solve them, produce the design, predict the design curve. If you can't do it, of course, you measure it. So now my next step of Levens-PL starts. I describe the chemistry to you. Here's how you write the reactions. A plus B goes to C, B plus C goes to whatever it is. There are a whole lot of reactions, doesn't matter. I can write as many as you want. I assume these reactions to be elementary. That means the rate of this reaction is first order with respect to T and first order with respect to C. I am going to make this assumption. Now I write balances. Okay, batch reactor, no input, no output, accumulation is equal to various rates. Because are there in the end. They are accumulating because one, a small size V can grow and produce the size you want, but a size V can grow and go out of size range. So this is a net effect of growth. Particles also can coalesce, they can become one. So if particles of size V are coalescing, they are going out of the range, that is its loss. Two small particles can coalesce and give you the right size, that is its production. And finally, they are being born at the nucleus size. Okay, that is its last term. Okay, so I solve all this. Very simple. I wrote equations except for population balance, everything else you know from Levens-PL. I have not used anything more than that. Okay, I solve these equations, and this is my model curve. Okay, this is a first model to predict nanoparticle size in any process. It was developed by us. Okay, and this is a first model. You see, it's not so very good in the end, but it's very good in the beginning. So my colleague Prof. Santosh Gupta has improved this model, and he has made the accuracy better, and used this model to make a continuous reactor to produce nanoparticles on a bigger scale. Batch reactor is never used for making big scale product. You have to have a continuous reactor. You got a centrifugal reactor to make these particles at a fairly good scale with a lot of improvement. Okay. Alert nucleation and growth is a new knowledge. I know Levens-PL, I think. So I combine these two and can produce this kind of graph for you, which is able to predict very nice things. Now I am going to move on to a totally different area. I am going to talk about energy. Okay. Now on one side, I talk to you about nanoparticles. There's plenty of room at the bottom, you know. Now I want to talk to you about energy. And this is what I've been doing for quite a while now. I'm going to talk about lead acid battery. Lead acid battery has been invented by Gaston Plante, is 150 years old. Really a very ancient battery. And it gives you a good voltage. Voltage is very important because current times voltage is power. Okay. The rate at which you are able to produce energy depends upon two things. One, current. Second is voltage. If a battery produces 1 volt, not a very good battery. A battery produces 2 volts, good. Battery produces 4 volts, excellent. That is lithium battery. But 2 is not bad. Another thing everybody worries about environment, lead can be fully recycled. Battery can be sent to a factory. In America, you cannot throw lead acid battery on the road. It's not possible. You want to buy a new lead acid battery, you got to return the old battery, so that lead can be fully recycled. There is a factory near Bangalore, in Malur, which can recycle batteries. Life is about 1,000 cycles, which is not bad. There are 2 disadvantages for this battery. Okay, it is very slow, very slow. You need almost 24 hours to charge this battery. Not a very good battery. Some of you will know Riva car, first electric car made in India. In the first version used lead acid battery. You require 24 hours to charge this battery. Not very good. Okay, who will spend 24 hours charging the battery? Another thing is to draw current also very difficult. If you draw very, very high current, it will stop immediately. Charging and discharging are very, very slow. That's a disadvantage. Battery, very heavy. Lead is a very, very high element material. So it's very heavy. So in Riva car, I think 1/3 of the weight came from the battery. So that's, you are wasting battery. You like to send passengers, not batteries, So it was a very bad design. But there's one more advantage which I have not mentioned. It is dead cheap. It is nearly 10 times as less expensive as lithium batteries. Bottom line, very good for lead acid battery. That's why people make lead acid batteries. Batteries are storage devices for electrical energy. So we have a chemical reaction. When this chemical reaction goes forward, there is a negative change in the free energy, that is discharge. That negative change in the free energy is directly converted to electrical energy. It's a direct conversion. Coal also has got chemical energy, but you burn it and generate energy. That's indirect conversion. Here, conversion is direct. That is why it's very efficient. Okay, there are many applications. Every UPS you see is lead acid battery. Every UPS battery you see, including telephone towers, whatever you see, is all lead acid batteries. It's a big business. They are starting lighting ignition battery in cars. That is, everybody who has seen a car will see this is a lead acid battery. There are some applications where intermittent energy sources can be stored, like solar energy is there. Is only there during daytime. During nighttime, nothing is there. But you can't shut off your power plant. So batteries are used to store electrical energy which you generate in the daytime in the form of battery. There is a 3.5 megawatt hour plant which uses lead acid battery, and discharge, as I told you, very slow. But large amount of energy can be stored. Now, I want you to notice again, I am going to begin with chemical reaction engineering approach. Where do we start? With chemistry. So, two insoluble solids, lead oxide and lead, react with sulfuric acid, produce lead sulphate, which is also an insoluble solid, and produce water. This is the overall chemical reaction. Lead sulphate is insoluble. Okay. So what it will do? It will precipitate. So you can guess, I am going to talk about nucleation and growth of lead sulphate particles. What is applicable in nanotechnology is also applicable in batteries, in unit operations, whatever, whenever there is a phase change, the same principles can be applied. Here is how electrical energy is generated. You have to do this chemical reaction a particular way. You have to generate an oxidation reduction pair out of this reaction. Only then you can generate electrical energy. So on one side, lead is oxidized to lead sulphate and 2 electrons. These electrons which flow through the external circuit come to the other side. You also notice when I produce 2 electrons here, 2 protons are produced, charge is completely balanced. 2 electrons have come here, they react with lead oxide and sulfuric acid, and protons which have come from here by diffusion, they produce lead sulphate and water. So charge is flowing in the external circuit in the form of electrons, that is current, and is being charge balanced by proton diffusion. Circuit is complete. So 2 insoluble solids producing another insoluble solid, that is a chemistry. Now, I want you to notice the chemical engineering here. Electrons are not soluble in water, okay, and ions do not enter electrodes, but ions and electrons both are forming. As soon as they form, they must divorce each other because they can't enter each other's space. Where can this reaction take place? At the interface. That is a catalytic reactor. Okay. So battery is a heterogeneous catalytic reactor, which is what you learn in later chapters of Lebensspiel. There is diffusion from reservoir. Therefore, this should look to you like 3 slabs in series which everybody solves in heat transfer problems. The only thing is I got 2 reactors which are separated by a diffusion barrier. So all I have to do is model this thing and I worry about the insoluble product. That is where nucleation and growth of a new phase comes. Now, these are electrodic reactions. Normally, you will write a chemical reaction in this manner. You can write A plus B goes to C, but the same thing you can write as A plus B minus C is equal to 0. The same thing. So, this is how chemical reactions are written. Now, if you have got electrodic reaction, electrons are also products. Therefore, reaction will have all these products and also ions. Okay. This is how you A naught. Then the concentration effects like first order, second order, whatever you want to write that. Then electrochemical reactions are also influenced by potential differences. So, that potential difference is written like this. And finally, if these are the active particles like lead or lead oxide, then lead sulfate, which is represented in color magenta, it is depositing on top of the active material. So, blocking active area available to you is decreasing. So, that is this coverage factor or fouling factor. Okay. You got a catalytic surface. Suppose carbon deposits on that, then that is not available for reaction anymore. You have to subtract that blocked area in order to get the proper area. Okay. I combine them with the rate loss. I am not going to bore you with this. It is a bit more complex than simple reactions. They are input and output